this part of the lesson, 33B, we're going to be exploring trigonometric ratios for angles that are greater than 90 degrees. Of course, not all angles are acute. So trigonometric ratios have been defined in terms of sides and acute angles of right triangles. Trigonometric ratios can also be defined for angles in standard position on a coordinate grid, and that's what we're going to be exploring. What is standard position? So standard position, an angle in Cartesian plane whose vertex lies at the origin and whose initial arm, the arm that is fixed, lies on the positive x-axis. So this would look like would be, there's my initial arm on the x-axis. The vertex is at the origin at 0, 0. So origin, which is your vertex. And then we would have the arm like such, and that would be the terminal arm. Okay, but we can move that arm into the different quadrants because we know that there are 4 quadrants on a grid. We also want to define what is the principal angle. So the principal angle, which is denoted as theta, the Greek symbol, the counterclockwise angle between the initial arm and the terminal arm of an angle in standard positions. Its value is between 0 and 360. And what we mean by that, it could be in the first quadrant, which is 0 to 90, second quadrant, 90 to 180. You can move that terminal arm into the third quadrant, which is between 180 and 270, and then back to a full circle between 270 and 360 in quadrant number 4. So the principal angle, again, if we were to draw that, would be, as we said, the counterclockwise angle. So it would be from the initial arm to the terminal arm, and that would be theta. Okay, so we would consider that the principal angle. And again, like we mentioned, we're going to take that terminal arm into the different quadrants and then determine measures of those principal angles. Okay, moving on, we also want to, as we're exploring, define what is a related acute angle. The acute angle between the terminal arm of an angle in standard position and the x-axis when the terminal lies in the other quadrants 2, 3, 4. It is also called the reference angle. So what that would be, if we put it into the second quadrant, so again, our principal angle coming all the way into the second quadrant, we'll call that theta. Then the related acute angle would be that measure, okay, and we also call the symbol beta for the related acute angle or that reference angle. So that is the related acute angle. And notice I drew that angle from that terminal arm straight down to the x-axis. Now, again, we're going to have that terminal arm in the different quadrants. It is always very critical to draw, again, that related acute angle is from the terminal straight down to the x-axis, so that vertical line to help you determine that related acute angle. So negative angles, we also want to know what that means. That means we are going to go clockwise. So negative angle is an angle measured clockwise from the positive x-axis. So to draw that, I would say let's draw one to the terminal arm is in the third quadrant. Okay, so if we had a negative angle, again, it would come this way. Okay, so again, always from the initial arm, and then we move that over. Now we're going clockwise. So in this case, for example, that could be something like negative 120 degrees because the angle is moving clockwise. And therefore, the related acute angle would be in here. And in this case, it would be 60 degrees because we know right up would be negative 180. That related acute angle is, and we always take the absolute value because you will see later on how that impacts. Okay, quadrantal angles, angles whose terminal arm lies on an axis. So sometimes we'll have a 0-degree angle, 90-degree angle, 180-degree angle, and 270-degree angle. So what we want to keep in mind are those points. So at 0, 0, we also want to indicate that the arm of the radius in this case is always 1. So if that's the case, if the radius is always 1 of the circle, as we're taking that terminal r to the different quadrants, if we land on the 90-degree angle, we know in this case x is 0 and then y would be 1. Okay, taking that around to 180 degrees. Well, in this quadrant, we know x becomes negative. So it would be negative 1 and 0. And then at 270 degrees, again, we know here x is 0, y would be negative 1. And we want to recall those coordinates when we have the terminal all lining up against either a 0-degree angle, 90 degree, 180, 270, and 360 degrees. Okay, moving on. To determine the value of an angle using the coordinate grid, the following applies. So we're always going to let x, y be the point on the terminal r of an angle in standard position. We're also going to look at the side opposite is y, and the adjacent side is always x. So using SOHCAHTOA, now we're putting it onto a grid. So now we can label it according to coordinates. Okay, so opposite is always going to be y, adjacent is x, and the hypotenuse is always that radius r. The side opposite is y and the adjacent side is x. As I said, the hypotenuse r can be found by using the Pythagorean theorem. So hence, if you're in quadrant 1, so if we just label it just for our sake, we know that the angle across it would be my hypotenuse, which now we're going to refer to as the radius. Across from our angle would be y, and x would be my adjacent. Now that we're putting SOHCAHTOA, these trig ratios, onto a grid, we want to apply, instead of using opposite, we know that's y. Instead of using adjacent, we know that is x. So how does that change our trig ratios? Well, if sine theta is opposite over hypotenuse, that would be y over r. Cosine is adjacent over hypotenuse, which would be x over r. Tan, of course, would be y over x, and then in this case, our radius would be 1. Okay, so let's try to apply this. Again, now we're giving coordinates on our terminal arm, so we're going to be giving it our x and y. As mentioned earlier, to determine the r value, we can use the Pythagorean theorem to determine that radius value. So the point 5 and 12, so let's plot that. 5x is 5, y is 12, is on the terminal arm of an angle theta in standard position. So let's, again, making sure that the vertex is at that origin 0, 0. Find its primary trig ratios. So I'm going to just indicate, you always want to create that right angle triangle. That's why we can use these trig ratios. So we know that x is 5, y is 12. We don't know the radius, but we can easily determine it using the Pythagorean theorem. So in theory, r squared is always going to equal to x squared plus y squared, because we know c squared, which is the hypotenuse, is equal to the other two sides, sum squared. So in this case, we can say r squared is equal to x is 5, y is 12, r squared would be 25 plus 144. So r squared is equal to 169. Taking the square root of both sides, r is always positive, which is 13. So the hypotenuse is 13. Okay, knowing again that sine theta, we're just going to write it out just for practice sake. It's always y over r. Cosine theta is equal to x over r. And tan theta is going to equal to 12 over 5. Oops, I'm already putting it in. Would be y over x, which we know is 12 over 5. So we can put that in. So sine theta, y, and I like to list what my coordinates are, so it's a little bit easier. So we have x is equal to 5, y is equal to 12, and r is equal to 13, which we calculated. So sine theta is y, which is 12 over 13. Cosine theta is equal to x, which is 5 over the radius 13. And then tan theta is equal to y, which is 12 over x, which is 5. And you would just leave it as a fraction. No need to put into decimal ever. We want to leave it as exact. So if the terminal arm lies in quadrants 2, 3, and 4, there exists a related acute angle and a principal angle. So the principal angle, as you look in the diagram to the right, is that red angle, and that beta angle is your related acute angle, or they often call it the reference angle. So finding the related acute angle beta in quadrants 2, quadrants 3, and quadrant 4, let's start with quadrant 2. What we want to remember is because we're using the coordinates now, depending on what quadrant we are, those coordinates will be impacted, whether they're going to be positive or negative. So when we move the so we're looking at the related cube, but when we move the principal angle into quadrant 2, we know all the values of x in quadrant 2 are negative. So we have to indicate that the coordinate for x is negative, y stays positive. Okay, and how is that going to impact our ratios? So keep in mind all those ratios that have an x in it will now become negative values. So sine theta would be, that's not impacted because it's y over r. Cosine, however, does get impacted. So it would be negative x over r, and tan would be y over negative x. Horizontal is positive, and that would be 1. So if we wanted that related acute angle, we know that the full angle from one quadrant 1 to quadrant 2 would be 180 degrees, but that difference from our principal angle is what the related acute angle value would be. So that means we would take 180 degrees and we would subtract theta. Okay, and that would give us the value for a related acute angle. Okay, so again, this is an investigation. What happens now when we move that terminal arm now into quadrant number 3? Now, looking at quadrant number 3, x coordinate is negative, and so is the y coordinate, and that will directly impact our ratios. So we know sine theta is negative y over r because in quadrant 3, y is negative. Then we look at cosine x. We know that x is negative in quadrant 3, so negative x over r, and tan would be negative y over negative x, which of course would reduce to being a positive y over x, because two negatives divided by each other is a positive. Now the radius always remains the same, which will be 1. So how do we determine the related acute angle in this case? So because we're all the way into the third quadrant, the beta angle, we would take whatever the principal angle is, subtract that by 180 degrees, because it is that difference between the x-axis to your principal angle. So we're going to say 180 subtracted from your angle. Okay, so whatever your principal angle is, the difference between 180 and that principal angle is what the related acute angle would be. Now moving into quadrant number 4. Okay, in this case, the x is positive, the y is negative in quadrant 4. So again, coordinates impact the ratio. So whichever ratio has a y in it will now become negative. So sine theta, which is negative y over r, cosine would be x over r, and tan would be negative y over x. R is still 1. Now, how do we determine that related acute angle? Again, the terminal arm being quadrant 4, the principal angle, that difference from 360 will give us our related acute angle. So we're going to take 360 degrees minus our principal angle theta. Okay, now let's put this into practice. We have determine the related acute angle beta for each angle theta. Sketch theta in standard position and label the related acute angle beta. So as you're getting started, just keep in mind, label your axes. So it's y and x, but we know this is 0 degrees, this is 90 degrees, this is 180 degrees, 270, 360. And you're just always going up by 90 degrees because each quadrant is 90 degrees. So 130 degrees. Well, we know from 0 to 180 would be from the first quadrant to second, but we're at 130. So that means we'd go 0 to 90, and we would end up here. Remember, the vertex is always at the origin. This would be theta, which is equal to 130. Now, again, because we are in quadrant number 2, we know the beta angle is going to equal to 180 minus your principal angle, which happens to be 130 degrees. So the beta angle is equal to 50 degrees. So beta is equal to 50 degrees. Okay, looking at the second example in B, 225. Again, label these 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then 360. So now we're going to end up into the third quadrant between 180 and 275. So theta here is equal to 225 degrees. Again, the related acute angle is the difference between the terminal to the x-axis. So you're always drawing that vertical line from your terminal arm, whether it's up or it's down, but you're going towards the x-axis. So we know that the difference between theta is equal to theta minus 180 when you're in quadrant number 3. So we're going to take 225 minus 180 degrees. So that related acute angle is 45 degrees. Excellent. And 315, again, I like to always label. So it gives me an idea for my angle. It's just easier to draw. Okay, so 315 is between 270 and 360. So we're going to make sure. Okay, remember the vertex is always at 0, 0, so you want to properly draw. Okay, so quadrant number 4, the related acute angle is always 360 minus your principal angle, so 360 minus 315. The related acute angle is 45 degrees. Now, moving into example number 3, we have sketch the terminal arm, find the expression for sine theta and cosine theta, and determine the principal angle theta and the related acute angle beta. Okay, so first thing we do, the sketch is always a good idea because we have that visual of what our angle looks like. So let's quickly do that. We know this is X, this is Y. So again, a quick little sketch. X is -3, so 1, 2, 3. Y is +2, so plotting that. Quick little sketch, but again, we want to make sure we have a visual of what's going on. So we have that our principal angle is in quadrant number 2 from here to here. So X is -3, Y is +2. So notice we need all three coordinates, both coordinates and the radius, I should say, which we can calculate using Pythagorean theorem. So we've done a quick little sketch. So we know this is my angle. So we need to determine the radius before we can state the ratios. Okay, so in order to state the parametric ratios, you need all three values, the x-coordinate, the y-coordinate, and the radius. So in this case, we know r squared is always equal to x squared plus y squared. So r squared is equal to -3 squared plus 2 squared. So r squared is going to equal to 9 plus 4. R squared is equal to 13. Radius is always positive, so radius is equal to the square root of 13. Please, please, please always leave these in exact form. No need to use decimals. So we know that sine theta is always y, which is 2 over r. Okay, don't forget to rationalize the denominator. So we do that by multiplying it by itself. So we know sine theta is going to equal to 2 root 13. Okay, and that gets rid of the radical in the denominator. So we always want to rationalize the denominator. Cosine theta is x, which is -3, over the radius, which is square root of 13. We rationalize that denominator. Multiplying it by itself. So we have -3 root 13 all over 13. Now, if you could reduce 3 over 13, you would, but because we can't, we leave it as exact. Please, 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 no decimals. Okay, so last we want to determine the principal angle theta and the related acute angle beta. So we want to make sure, again, we know based on our knowledge of our quadrants, we know 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees. Okay, so keep that in mind always. So we're going to say for C, C, we're going to say cosine theta is equal to a -3 root 13 all over 13. Now, again, as we learned earlier, when we need to determine the angle, we're going to have to bring the cos over to the right. So we're going to say theta is equal to the inverse of cos. So which is equal to 146 degrees. We'll run to the nearest degree just to make things simplified. Okay, so we did rounds, we're going to say about. Okay, so that's the principal angle theta, which is 146 degrees. So we know this is about 146. Okay, because our principal angle is in the second quadrant, we know to figure out the beta angle, we would say beta angle is going to equal to 180 minus my principal angle. So beta is going to equal to 180 degrees minus 146 degrees is about 34 degrees. Okay, last but not least, we have example 4. If sine theta is equal to 5 over 13, and the terminal arm is in quadrant 1, determine the other two primary trigonometric ratios. So this time we're getting the sine ratio. We know the sine ratio is y over r. So this is y, this is r. Okay, so again, quick little sketch. We know it's told us it's in quadrant 1. So y is 5. So 1, 2, 3, 4, 5. Okay, so we don't know where x is, but I'm just sketching it out for myself. Again, it's very, very critical to have a sketch of where your principal angle would be, and that way we can calculate the related acute angle quickly. Now, again, we use the Pythagorean theorem when we had the x and y coordinates, but likewise, if in the ratio we're given the y coordinate and the radius, we can use the Pythagorean theorem to figure out the unknown coordinate. So we know r squared is equal to x squared plus y squared, r is 13. X we don't know, and we know that y is 5 squared. So 13 squared. So we're going to, if we isolate for x squared, it's going to be 13 squared minus 5 squared. Okay, so x squared is equal to 169 minus 25. X squared is going to equal to 144. Take the square root of both sides. X is going to equal to 12. Okay, so we know y is 5, x is 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 12. Y is 5. Oops. Quick little sketch. Again, right, so we know that is our principal angle. This was y is 5, x is 12. So notice x is positive. It's in that first quadrant. Okay, so technically we know when to take this root, it could be either, but it's in the question it says quadrant 1. Okay, so with that, because we now have x is 12, 5 is your y, and r is 13, we can determine the other primary trigonometric ratios. We know that sine theta, I'm just going to rewrite that, sine theta is equal to y over r, which is 5 over 13. Cosine theta is x over r, which is 12 over 13, and tan theta is y over x, which is 5 over 12. So just a reminder, sine theta, y over r, cos theta is x over r, and tan theta is y over x.